Look up at the night sky, and what do you see? Stars, galaxies, maybe the faint glow of the Milky Way, but there's something invisible, something far stranger painting the darkness with secrets we're only beginning to unravel. A ghostly sea of X-rays floods the cosmos, an eerie light we can't see with our eyes, yet it's everywhere, threading through the vast emptiness of space. This is the cosmic X-ray background, a mysterious glow that has puzzled scientists for decades. Where does it come from? What cosmic engines could possibly be churning out this relentless, unseen energy? The answers, or rather, the lack of them, lead us down a rabbit hole of 25 astonishing mysteries, each more bewildering than the last. Imagine every X-ray telescope ever built turning their gaze upward, scanning the heavens, only to find this faint, uniform haze stretching across the universe. At first, it seemed like noise, static in the cosmic signal, but the deeper we looked, the clearer it became. This wasn't just interference. This was a message, a cosmic whisper hinting at forces and phenomena beyond our wildest theories. Some of these X-rays come from superheated gas swirling around black holes, others from the explosive deaths of stars, but together they form a tapestry of questions. Why does this glow persist in places where there are no visible sources? What hidden structures, what invisible giants are lurking in the shadows of the universe, bathing everything in this high-energy light? This isn't just about filling in gaps in a textbook. It's about rewriting entire chapters of astrophysics. The cosmic X-ray background is a puzzle wrapped in an enigma, and solving it could reveal everything from the birth of supermassive black holes to the hidden architecture of the universe itself. Over the course of this journey, we'll uncover 25 of these mind-bending mysteries, some so strange they challenge the very laws of physics as we know them. So buckle up, we're about to become cosmic detectives, piecing together clues from the farthest reaches of space and time, hunting for answers in the invisible light that surrounds us all. The very first puzzle that left scientists baffled was this. Most of the cosmic X-ray background doesn't come from any visible object. When early X-ray satellites like Uhuru and later Rosat scanned the sky, they expected to see pinpoint sources, active galaxies, black holes, star clusters, all easily mapped and accounted for. Instead, they found something far stranger, a soft, almost uniform haze of X-rays stretching across the entire sky, like a fog that refused to clear. No matter where they looked, the glow persisted, faint but undeniable. This was more than just a technical challenge. It was a cosmic contradiction. Known X-ray sources, no matter how numerous or powerful, couldn't explain the sheer scale of this emission. Think of it like walking into a dark room expecting to see a few scattered light bulbs, only to find the entire space bathed in an eerie, sourceless glow. Where was all this energy coming from? Some suggested it might be the remnants of countless dead stars, their final bursts of radiation echoing through space. Others theorized swarms of invisible black holes, too small or distant to detect directly, yet collectively flooding the universe with X-rays. Then came a breakthrough. Deeper observations revealed that a fraction of this glow could be resolved into individual sources, distant supermassive black holes in young, voracious galaxies, their feeding frenzies emitting X-rays that had traveled billions of years to reach us. But even after accounting for these, a significant portion of the background remained stubbornly diffuse. That meant something else, something more exotic was at play. Perhaps vast reservoirs of superheated gas, left over from the universe's violent infancy, were still radiating energy across the cosmos. Or maybe entirely new classes of cosmic objects, ones we haven't even imagined yet, were hiding in plain sight, their faint whispers blending into the X-ray sea. Every answer led to new questions. If hot gas was the culprit, why wasn't it clumping into visible structures? If unseen black holes were responsible, how did they form so abundantly in the early universe? The deeper astronomers dug, the more they realized the cosmic X-ray background wasn't just a mystery, it was a mirror, reflecting our own ignorance about the universe's hidden workings. And the most thrilling part, we're still scraping the surface. But here's where things get even stranger. If supermassive black holes are the universe's X-ray powerhouses devouring matter and spewing high-energy light, then why are we still coming up short? The math just doesn't add up. Even after tallying every known active galaxy and quasar, the cosmic X-ray background remains far brighter than it should be. It's like counting every light bulb in a city at night, only to realize the sky is still glowing twice as bright as your calculations predicted. So where's the missing energy coming from? One tantalizing possibility is that the universe is teeming with black holes we simply can't see. Not the blazing behemoths at the centers of galaxies, but quieter, stealthier giants, black holes in hibernation. Picture a dormant volcano, silent for centuries but still capable of eruption. These black holes might not be actively feeding, but when they occasionally snack on passing gas or stars, they could flare up just enough to contribute to the X-ray fog. Another theory suggests entire populations of mid-sized black holes, too small to dominate their galaxies but numerous enough to collectively leave a mark. Imagine scattering thousands of embers across a dark field, individually faint, but together they'd cast an eerie glow. Then there's the elephant in the room. What if we're missing something far bigger? Some astronomers speculate that early in the universe's history, supermassive black holes formed in ways we don't yet understand, perhaps collapsing directly from massive gas clouds, skipping the usual star death process. These direct collapse black holes could have littered the cosmos long before galaxies took shape, seeding the universe with X-rays that still linger today. Others wonder if dark matter, the universe's most elusive ingredient, might play a role. Could certain types of dark matter particles decay or collide, releasing X-rays as a byproduct? It's a wild idea, but when faced with a mystery this profound, even the wildest theories deserve a hearing. The deeper we dig, the clearer it becomes. The cosmic X-ray background isn't just missing a few puzzle pieces. It's hinting at entire chapters of black hole history we've yet to read. Every time we think we've accounted for one source of X-rays, another gap appears, pulling us further down the rabbit hole of cosmic secrets. And that's what makes this mystery so thrilling. It's not just about what we know we don't know. It's about what we don't even know we don't know. Deep in the cosmic shadows, entire galaxies hide in plain sight, not behind dust or distance, but by design. These are the universe's stealthiest powerhouses, galaxies so heavily shrouded in gas and dust that their visible light is smothered, yet their X-rays scream into the darkness. For decades, we had no idea they existed. Then, X-ray telescopes peeled back the veil, revealing a hidden population of active galactic nuclei, supermassive black holes gorging on matter. That could solve a major piece of the cosmic X-ray background puzzle. But finding them, that's where the real challenge begins. Picture a lighthouse wrapped in thick fog. The beam of visible light gets swallowed by the haze, but if you could see in X-rays, the lighthouse would shine through effortlessly. That's exactly what's happening with these obscured AGN. Their central black holes are feasting so violently that the energy should make them among the brightest objects in the sky, but the surrounding dust clouds absorb nearly all their optical and ultraviolet light. Only the highest energy X-rays punch through, leaving a faint fingerprint in the cosmic background. Early X-ray missions detected this glow but couldn't pinpoint the individual sources. It was like hearing a choir of voices through a wall. You know the singers are there, but you can't count them or tell who's off-key. Then came Chandra and XMM Newton, two telescopes with the precision to isolate these whispers. They revealed thousands of previously invisible AGN, each buried in the heart of a galaxy we'd overlooked. But here's the twist: even these advanced observatories struggle to catch the most deeply hidden ones. Some black holes are so obscured that even X-rays get partially absorbed, leaving only the hardest, most penetrating radiation to escape. Detecting these requires crossing astronomical detective work, combining X-ray data with infrared surveys to spot the heat from the dust itself. It's like tracking a criminal by their shadow and their footprint at the same time. The implications are staggering. If enough of these hidden AGN are out there, they could account for a significant chunk of the cosmic X-ray background's unresolved glow. But their existence also raises new questions. Why are some galaxies so much dustier than others? Do these black holes grow differently, or are we seeing a fleeting phase in their evolution? Every discovery peels back another layer, revealing just how much we've underestimated the universe's hidden players. And with each answer, the cosmic X-ray background becomes less of a mystery and more of a treasure map. Now imagine mapping the universe's X-ray glow like a cosmic weather system, expecting storms and quiet patches to follow the visible galaxies, only to find the brightest clusters forming patterns no one predicted. The cosmic X-ray background doesn't just glow uniformly. It clumps in ways that defy logic, gathering in vast, invisible structures that don't align with the galaxies we see. This isn't just a quirk, it's a glaring mismatch between the universe's hidden skeleton and its visible flesh. Take a sheet of paper and sprinkle it with iron filings. They'll arrange themselves along the lines of a magnet's field, revealing forces you can't see. The cosmic X-ray background does something similar, tracing the gravitational pull of dark matter's hidden scaffolding. But here's the strangest part. Some of the brightest X-ray clusters appear where there's almost no visible matter to fuel them. It's like stumbling upon a bustling city in the middle of an empty desert, its skyline glowing with energy but its streets eerily vacant. How can such intense X-ray emissions come from places that look like cosmic ghost towns? One leading theory points to dark matter's gravitational grip. Picture an invisible hand gathering intergalactic gas into vast, unseen reservoirs. As this gas piles up, it heats to millions of degrees, glowing in X-rays, yet the hand itself remains hidden. Some simulations suggest these clusters could be the remnants of ancient cosmic collisions, where dark matter's gravitational wake funnels gas into dense pockets. Others propose that supermassive black holes flung into the voids during galactic mergers might be dragging hot gas with them, lighting up the darkness like lone campfires in the wilderness. But the plot thickens. Certain clusters show X-ray intensities that don't just mismatch visible matter. They outright contradict predictions. In some regions, the gas is hotter than models allow, as if an unseen furnace keeps cranking the temperature. Could decaying dark matter particles be injecting extra energy, or are we witnessing the echoes of primordial turbulence left over from the universe's fiery birth? The more we study these clusters, the clearer it becomes. They're not just anomalies. They're signposts to something fundamental we're missing about how matter, both seen and unseen, shapes the cosmos. Every new observation peels back another layer, revealing how little we truly grasp about the forces stitching the universe together. The cosmic X-ray background's clustering isn't just a mystery, it's a challenge, daring us to rethink the maps we've drawn of reality itself. And the deeper we look, the more the universe whispers back, "You haven't found all the pieces yet." Scientists expected the cosmic X-ray background's energy signature to follow a predictable curve, a smooth slope matching known sources like black holes and supernova. Instead, they found jagged edges, unexpected peaks and valleys in the spectrum, as if someone had taken a pair of cosmic scissors to the data. This isn't just a minor discrepancy. It's a glaring anomaly that suggests entire classes of X-ray sources might be missing from our celestial inventory. Think of it like tuning a radio and stumbling upon a frequency that shouldn't exist, a station broadcasting between the channels, defying the laws of transmission. The CXB's spectrum shows too many soft, low-energy X-rays, and not enough of the hard, high-energy ones we'd expect from typical black hole emissions. It's as if the universe has been quietly running an unlicensed X-ray generator, pumping out photons with energies that don't fit any known astrophysical recipe. Some researchers initially blamed incomplete data, assuming better telescopes would smooth out the bumps. But when Chandra and XMM Newton delivered crystal-clear readings, the irregularities only became more pronounced. One leading explanation points to a hidden population of warm, hot intergalactic matter, a diffuse ocean of gas heated to millions of degrees but too thin to see directly. Picture steam rising from a highway after a summer rain. It's there, but it doesn't form distinct clouds. This gas could absorb and re-emit X-rays at specific energies, potentially explaining some of the spectral quirks. Yet even this can't account for the full mismatch. Another suspect, ultra-faint galaxies teeming with X-ray binaries, pairs of stars where one siphons material from the other, creating sporadic bursts of X-rays. Individually, these systems would be too dim to spot, but collectively, they might skew the background's energy signature. Then there's the wild card, decaying dark matter. Certain theoretical particles, like sterile neutrinos, could produce X-rays at precise energies as they break down. If these particles exist, their decay signature might be woven into the CXB's spectrum like a hidden thread in a tapestry. It's a radical idea, but the spectrum's odd notches align eerily with some dark matter models. Of course, this raises bigger questions. Why haven't we detected these particles elsewhere? The spectrum's stubborn complexity forces us to confront an uncomfortable truth. We might not just be missing a few sources, we could be overlooking entire cosmic phenomena. Every unexplained peak and trough is a breadcrumb leading to physics we haven't yet imagined. And until we solve this puzzle, the universe's X-ray lab remains half its doors locked, its most fascinating experiments just out of view. For all our cosmic cartography, we've somehow misplaced half the universe's normal matter, not dark matter, the stuff that makes up stars, planets, and you vanished without a trace. Cosmologists call this the missing baryon problem, and it's one of the most embarrassing gaps in our understanding of the cosmos. We know how much normal matter should exist from studying the afterglow of the Big Bang, yet when we tally up everything visible, galaxies, gas clouds, even the dust between stars, we're coming up shockingly short. Where is it all hiding? The cosmic X-ray background might be holding the key, pointing to a shadowy realm of superheated gas strung between galaxies like cosmic spider silk. This isn't some minor accounting error. The missing matter amounts to roughly 50% of all baryons, the particles that build atoms that should be out there. Early theories suggested it could be lurking in cold, dark pockets, invisible to our telescopes. But when astronomers calculated how much gas would need to be hiding that way, the numbers didn't add up. Then came a breakthrough. X-ray observations hinted at a vast, seething ocean of warm, hot intergalactic medium, or WIM, threading the voids between galaxies. Picture steam rising from a boiling pot, too diffuse to see as liquid, but unmistakably there when you look closely. This gas isn't cold or dark. It's scorching at temperatures between 100,000 and 10 million degrees, glowing faintly in X-rays. Here's where the cosmic X-ray background becomes a treasure map. The WIM extreme heat means it doesn't emit much visible light, but it does leave fingerprints in the high-energy spectrum. Certain wavelengths in the CXB show absorption lines, tiny dips in the X-ray glow where the WIM has soaked up specific energies, like a sponge selectively absorbing water. Finding these lines is like listening for echoes in a cavern. The subtle distortions reveal the shape and density of the hidden gas. Some of the strongest evidence comes from quasars, whose brilliant X-ray beams pierce through the WIM, allowing us to measure its composition billions of light years away. Yet the WIM isn't just floating passively. Simulations show it's woven into a cosmic web, funneled along filaments of dark matter that stretch across the universe. These filaments act like highways for gas, guiding it into galaxy clusters or leaving it stranded in the voids. The problem: this gas is so tenuous that even our best X-ray telescopes struggle to detect it directly. It's like trying to photograph fog with a flashlight. The beam passes right through without a clear reflection. That's why the CXB's diffuse glow is so crucial. It's the aggregate signal of countless WIMP strands, each too faint to see alone but collectively impossible to ignore. But there's a twist. Some of the missing baryons might not even be in the WIMP. Recent studies suggest a fraction could be trapped in enormous, low-density halos around galaxies, like invisible atmospheres stretching far beyond their visible edges. Others might be tied up in dark galaxies, failed star-forming regions so dim they evade optical detection, yet rich in X-ray emitting gas. Even more tantalizing is the possibility that some baryons have been pushed out of galaxies entirely, blasted away by supernova or black hole jets into the intergalactic void, where they linger as ghostly ionized clouds. The cosmic X-ray background is more than a mystery. It's a bridge between the seen and unseen universe. Every unexplained wisp of X-ray light could be a strand of the WIMP, a lost baryon waiting to be counted. And with each new observation, we're not just solving a puzzle, we're rewriting the inventory of reality itself, one high-energy photon at a time. The cosmic X-ray background isn't just a static glow, it flickers. And that shouldn't happen. Diffuse light, by definition, comes from countless sources blending into a steady haze, like the combined glow of a city's skyline from miles away. But when astronomers trained their telescopes on the CXB over months and years, they caught something bizarre, patches of it brightening and dimming, as if hidden searchlights were sweeping across the universe. These fluctuations aren't just subtle tweaks. Some regions shift by as much as 20% in mere months. For a phenomenon spread across billions of light years, that's like watching the ocean's surface ripple in seconds. So what could possibly cause such rapid changes in something so vast? One explanation points to ultra-luminous X-ray sources, rare, erratic objects thought to be intermediate mass black holes on feeding sprees. These cosmic gluttons gulp down gas in violent bursts, flaring up unpredictably. Imagine a power grid where a few rogue stations randomly surge, briefly outshining the rest. But here's the catch: even these extreme objects shouldn't account for the scale of variability we're seeing. Their flares are too localized, too fleeting to shift the entire background's needle. Then there's the tantalizing prospect of echoes. When a supermassive black hole erupts, its X-rays can bounce off nearby gas clouds, creating delayed signals that masquerade as time variability. Picture shouting into a canyon and hearing your voice return moments later, except here, the canyon is a galactic core and the echo takes years to reach us. Yet even this elegant solution falters under scrutiny. The echoes would need to align with near impossible precision across vast distances to mimic the observed fluctuations. The real head-scratcher: some fluctuations occur in regions devoid of obvious energy sources. No active galaxies, no star clusters, just empty space throbbing with phantom X-rays. One radical theory suggests we're seeing the fingerprints of cosmic strings, hypothetical, galaxy-sized defects in spacetime left over from the Big Bang. As these strings vibrate or snap, they could release violent bursts of energy, briefly illuminating the X-ray background like lightning flickering behind a curtain. Or perhaps the answer lies in the unseen mechanics of dark matter. Certain models predict that when dark matter particles collide, they annihilate in bursts of high-energy radiation. If these collisions occur in dense, invisible halos around galaxies, they might flare up just enough to tweak the CXB's glow. It's a long shot, but when faced with a universe that refuses to follow the rules, even the wildest ideas deserve a seat at the table. Every flicker in the cosmic X-ray background is a breadcrumb, a clue that the universe is far more dynamic, far more mischievous than we ever imagined. And until we solve this enigma, we're left staring at the shadows, wondering what invisible hands are twisting the dials of reality itself. Right in our cosmic backyard, a mystery lurks, one that challenges how we understand our own galaxy's role in the grand X-ray tapestry. The Milky Way isn't just a glittering spiral of stars. It's cocooned in a gargantuan halo of superheated gas, stretching hundreds of thousands of light years into the void. This halo, seething at millions of degrees, should be a textbook contributor to the cosmic X-ray background. But when scientists try to quantify its glow, the numbers spiral into chaos. Some measurements suggest it's a dominant player, while others claim it's barely a whisper. Why can't we pin down something so close to home? Start with the halo's origins. Theory says it's a relic of the Milky Way's violent youth, gas blasted outward by ancient supernova and black hole eruptions, then heated to X-ray, emitting temperatures as it fell back into the galaxy's gravitational embrace. Picture a steamy exhale after a sprint lingering around the runner. Satellites like XMM Newton and Chandra have mapped this halo, revealing a patchy, asymmetrical structure, thicker near the galactic center and wispy at the edges. But here's the problem. The halo's X-ray brightness fluctuates wildly depending on where you look. Point a telescope toward the galaxy's crowded core, and the signal drowns out the halo's faint emission. Aim it at the sparse outskirts, and the halo's glow becomes clearer, but so does the contamination from distant quasars and foreground stars. It's like trying to measure the humidity in a room while someone keeps opening windows. The discrepancies grow stranger when we compare observations to simulations. Supercomputers modeling the Milky Way's evolution predict a halo that should outshine most of the cosmic X-ray background at certain energies. Yet real-world data often show the opposite. Our halo's contribution is frustratingly muted. One explanation: the gas might be clumpier than models assume, with dense pockets emitting X-rays efficiently while vast regions remain too diffuse to detect. Imagine a fog that's thick in some patches and barely there in others. Your estimate of its opacity depends entirely on where you stand. Then there's the solar system's own interference. The heliosphere, a bubble of charged particles blown by the sun's wind, scatters and absorbs some of the incoming X-rays, subtly distorting our measurements. It's as if we're trying to study a distant landscape through frosted glass, with the frost pattern changing as the sun moves through the galaxy. Even the Milky Way's magnetic field plays tricks, bending the paths of X-ray photons and muddying their origins. But the most tantalizing possibility is that we've underestimated the halo's complexity entirely. Recent studies suggest it might be stratified, with multiple layers of gas at different temperatures and densities, each emitting X-rays in distinct ways. Some layers could be leftovers from galactic collisions, traces of smaller galaxies the Milky Way cannibalized over eons. Others might be fueled by ongoing star formation, with stellar winds pumping fresh gas into the halo like a slow-motion geyser. Untangling these components isn't just academic, it's key to solving the larger puzzle of the cosmic X-ray background. If our own galaxy's halo is this poorly understood, how can we trust our maps of the universe beyond? Every conflicting measurement forces us to confront an uncomfortable truth. The Milky Way isn't just a bystander in the cosmic X-ray story. It's an active participant, its halo a dynamic, ever-shifting entity that refuses to fit neatly into our models. And until we crack its code, the cosmic X-ray background will keep one of its most persistent secrets hidden not in the depths of space, but right here at home. Astronomers once thought solving the cosmic X-ray background would be like completing a jigsaw puzzle. Identify enough individual sources, and eventually the full picture would snap into place. But after decades of observation, we've hit a wall. Even after cataloging millions of X-ray point sources, black holes, neutron stars, flaring galaxies, we've barely accounted for half the total flux. The rest, a gaping void in our understanding where the math stubbornly refuses to add up. Take NASA Chandra Deep Field observations, some of the most sensitive X-ray images ever captured. They reveal a sky peppered with active galactic nuclei, quasars, and star clusters, each a brilliant pinprick in the high-energy darkness. Yet when scientists tally their combined emissions, the numbers fall shockingly short. It's as if you counted every light bulb in a city, only to realize they're powering just 40% of the glow. So where's the other 60% coming from? One leading theory suggests we're missing a hidden population of faint, diffuse sources. Picture trying to census a forest by counting only the tallest trees. You'd overlook the underbrush, the saplings, the moss clinging to rocks. Similarly, X-ray telescopes might be blind to entire classes of dim or fleeting emitters. Dwarf galaxies with modest black holes, orphaned neutron stars drifting between galaxies, or even the collective sigh of millions of aging white dwarfs. Some simulations hint that these overlooked sources could fill the gap if only we had telescopes sharp enough to spot them. But there's a catch. Even if every faint source were accounted for, their emissions should follow predictable patterns, specific energy distributions tied to their physics. The cosmic X-ray background spectrum, however, shows excesses at certain energies that don't match known populations. It's like hearing a symphony where half the instruments are playing notes no composer ever wrote. This mismatch has led to wilder ideas. Could primordial black holes forged in the chaos of the Big Bang be evaporating in bursts of X-rays? Or are we seeing the collective glow of action's hypothetical particles that might convert to X-rays in the tangled magnetic fields of galaxy clusters? The most unnerving possibility, we're not just missing sources, we might be misreading the universe's X-ray recipe entirely. Some models propose that black holes in the early universe grew differently, their accretion disks emitting X-rays in ways that defy modern analogs. Others suggest the background's unresolved portion isn't from discrete sources at all, but instead a previously unknown form of diffuse emission, perhaps from decaying dark matter or vast shock waves left over from the cosmos's most violent collisions. Every unanswered photon in this equation is a whisper from the unknown, a reminder that our maps of the high-energy universe are still riddled with blank spaces. And until we solve the source count mystery, we're left with an unsettling truth. The universe might be far richer, far stranger than our telescopes have yet revealed. Among the most enigmatic players in the cosmic X-ray drama are the ultra-luminous X-ray sources, or ULCs, objects so fiercely bright they defy conventional astrophysics. Imagine a single cosmic lighthouse outshining an entire galaxy, blasting X-rays with the energy of millions of suns. These aren't supermassive black holes, nor are they typical stellar remnants. They're something in between, and their sheer intensity makes them prime suspects in the cosmic X-ray background's unsolved case. Yet the more we study them, the more they resist easy classification, leaving scientists scrambling to rewrite the rules of high-energy astrophysics. At first glance, ULXs should be straightforward. Their luminosity, up to thousands of times brighter than ordinary X-ray binaries, suggests they're powered by intermediate mass black holes, the elusive middleweights between stellar black holes and supermassive giants. But when astronomers zoom in, the story unravels. Some ULXs pulse like cosmic strobe lights, a telltale sign of neutron stars, not black holes. These ultra-dense stellar corpses shouldn't be capable of such extreme emissions. Their magnetic field should stifle the energy output long before it reaches ULX levels. Yet there they are, flouting the limits like cosmic overachievers. How, one theory suggests they're super-Eddington accretas objects feeding so voraciously that radiation pressure can't repel the infalling matter, creating a chaotic, superheated frenzy. Picture trying to extinguish a bonfire with a garden hose, only to have the water turn into more fuel. But ULXs have another trick up their sleeves. Their distribution makes no sense. They're often found far from galactic centers, lurking in star-forming regions or even isolated voids. If they were intermediate mass black holes, they should have migrated inward over time, drawn by gravity. Instead, they're scattered like cosmic nomads, suggesting they might not be black holes at all. Some could be exotic binaries where a neutron star or small black hole orbits a massive companion, siphoning material at unprecedented rates. Others might be stellar mass black holes caught in rare, hyper-efficient feeding modes, their X-ray beams amplified by relativistic jets pointed straight at Earth. The real puzzle, ULXs might be chameleons. Observations suggest some switch between different emission states, flickering between ULX and ordinary X-ray binary behavior. This volatility makes them maddeningly hard to pin down. Are they a single class of objects or a grab bag of astrophysical oddballs masquerading under one label? Compounding the confusion, their contribution to the cosmic X-ray background is equally murky. While individual ULXs are dazzling, their overall numbers are too sparse to explain the CXB's unresolved glow. Unless, that is, we're missing a hidden population of dormant ULXs, flaring up only intermittently across cosmic time. The irony is delicious. The very objects that should help solve the cosmic X-ray background's mysteries are deepening them instead. With each discovery, ULXs stretch our understanding of how matter behaves under extreme conditions, challenging the boundaries between known physics and cosmic anomalies. And until we crack their code, they'll remain both tantalizing clues and confounding red herrings in the hunt for the universe's missing X-rays. The cosmic web is the universe's grandest architecture, a vast, invisible skeleton of dark matter filaments stretching billions of light years, with galaxies clinging to them like dewdrops on a spider's silk. Theory says these filaments should be threaded with superheated gas, glowing faintly in X-rays as they snake through the void. If we could see this radiation, it would reveal the cosmic web's hidden structure in stark relief. But here's the catch. After decades of searching, the X-ray signature of these filaments remains maddeningly elusive, buried in the cosmic X-ray background's fog. Why is something so fundamental so hard to find? Start with the gas itself. Simulations predict these filaments should be scorching at temperatures between 10,000 and 10 million degrees hot enough to emit soft X-rays, but so diffuse that their signal drowns in the background noise. It's like trying to spot a single lit match from an airplane window while flying over a city at night. The faint glow of the filaments isn't just competing with brighter X-ray sources, it's also contending with our own galaxy's emission, interstellar dust, and even the solar wind's interference. Isolating the cosmic web's whisper requires peeling back layer after layer of cosmic static, a task even the most advanced telescopes struggle with. Yet there are tantalizing hints. In 2017, astronomers using ESA's XMM Newton telescope reported a possible detection of a faint X-ray signal aligned with a filament connecting two galaxy clusters over 50 million light-years apart. The energy of the emission matched predictions for warm, hot intergalactic gas, and its location traced the expected path of dark matter's gravitational scaffolding. It was like catching a glimpse of a ghost shadow just for a moment, but follow-up observations yielded conflicting results. Some teams claimed the signal was statistical noise, others argued it was real but contaminated by foreground sources. The debate rages on, highlighting just how fiendishly difficult this hunt truly is. Part of the challenge lies in the filament's unpredictability. Unlike galaxies or black holes, which concentrate their energy in discrete points, the cosmic web's gas is spread astonishingly thin, perhaps just a few atoms per cubic meter. Its X-ray emission isn't a steady hum but a patchy, irregular flicker, varying with local density and temperature. Some regions might shine brightly where filaments intersect, forming cosmic crossroads of hot gas. Others could be nearly dark, their gas too tenuous or too cool to detect. Mapping this requires not just sensitivity but luck, catching the web in the right orientation with enough overlapping filaments to amplify the signal above the noise. Then there's the problem of perspective. From Earth, distant filaments overlap in our line of sight, blending their signals into an indecipherable tangle. It's like trying to untangle a pile of transparent wires by staring at their shadows. To confirm the cosmic web's X-ray fingerprint, we'd need to measure its redshift, the stretching of light that reveals how far away the gas is. But detecting redshift in such faint, diffuse X-rays is like trying to measure the pitch of a whisper from across a crowded stadium. Current instruments lack the precision, though next-generation telescopes like Athena or Lynx might finally crack the code. The stakes couldn't be higher. If the cosmic web's X-ray glow is real, it would confirm a cornerstone of cosmology that dark matter's gravitational pull shaped the universe's large-scale structure, with ordinary matter following its lead. It would also solve a chunk of the missing baryon problem, locking down the whereabouts of the universe's lost atoms. But if the signal remains forever elusive, we might be forced to reconsider something even more radical. Whether our models of gas heating and distribution are fundamentally flawed, or if the cosmic web is far stranger than we've dared to imagine. For now, the filaments remain ghosts in the X-ray machine, their presence inferred but not yet proven. Every unexplained wisp in the cosmic X-ray background could be a strand of this hidden web, a thread connecting the universe's grand design. And until we tease it out, the cosmic web's greatest trick isn't hiding its existence. It's revealing just how much we still have to learn. Rewind the cosmic clock to the universe's infancy, and the cosmic X-ray background transforms into something unrecognizable, a thick, pervasive fog of high-energy light bathing everything in its glow. The farther back we look, the brighter this ancient X-ray haze becomes, defying all expectations about how the first galaxies and black holes should have behaved. It's as if the early universe was buzzing with X-ray activity long before the ingredients for such intense emissions should have existed. The clues come from quasars' lighthouses of the young cosmos, whose light has traveled over 12 billion years to reach us. As their X-rays pierce through intergalactic space, they pick up traces of the ambient radiation from that era. What these signals reveal is astonishing. The early universe wasn't just peppered with X-ray sources, it was saturated with them, producing up to 10 times more high-energy light than modern galaxy formation models predict. Picture walking into a nursery expecting to hear a few babies cooing, only to find the room roaring with the noise of a rock concert. Where did all this energy come from? One leading suspect is a generation of hyperactive black holes growing at breakneck speeds in the cosmic dawn. Today's supermassive black holes take billions of years to form, but in the early universe, some might have ballooned to staggering sizes in just a few 100 million years, a blink on cosmic timescales. These precocious giants would have gorged on gas and stars, belching out X-rays that flooded the young cosmos. But here's the catch: black holes that massive shouldn't have had time to form under normal circumstances. Their existence hints at exotic physics, like direct collapse black holes, monsters born not from dying stars, but from the sudden implosion of massive gas clouds skipping the star-forming stage entirely. Yet black holes alone can't explain the full intensity of the early X-ray fog. Another piece of the puzzle comes from star-forming galaxies, which in the early universe were hotter, denser, and more turbulent than their modern counterparts. Their young, massive stars lived fast and died violently, exploding as supernova that heated surrounding gas to X-ray, emitting temperatures. Add to this the possibility of abundant X-ray binaries, pairs of stars where one siphons material onto a neutron star or black hole, and you have a recipe for a universe crackling with high-energy light. But the plot thickens when we compare these observations to simulations. Cosmological models struggle to reproduce the sheer volume of X-rays detected at high redshifts. Either we're missing a key ingredient in our equations, like a previously unknown population of ultra-compact galaxies, or the early universe processed energy in ways we haven't accounted for. Some theorists even speculate that dark matter interactions might have played a role, with certain particle decays releasing bursts of X-rays that contributed to the primordial glow. What makes this mystery so pivotal is its implications for galaxy evolution. X-rays don't just illuminate the cosmos, they shape it. Their intense radiation can sterilize entire regions of space, suppressing star formation by ionizing gas before it can collapse into new stars. If the young universe was indeed this X-ray bright, it would rewrite the timeline of when and how galaxies could mature. The cosmic X-ray background's ancient fog isn't just a curiosity. It's a high-energy fingerprint of the universe's most formative era, challenging us to rethink how everything from black holes to dark matter conspired to build the cosmos we see today. Theoretical models of the universe have a glaring blind spot when it comes to energy specifically, the way black holes should have superheated intergalactic space over billions of years. Based on everything we know about accretion physics, the combined X-ray output from active galactic nuclei over cosmic history should have pumped enough energy into surrounding gas to raise its temperature dramatically. Yet when astronomers measure the warmth of intergalactic matter today, it's far cooler than simulations predict. It's as if the universe has a hidden thermostat, silently dialing down the heat we expected to find. The cosmic X-ray background might hold the key to this discrepancy, revealing gaps in our understanding of how energy flows through the cosmos. Take the case of quasars, those brilliant beacons powered by supermassive black holes guzzling matter at incredible rates. Their X-ray emissions are so intense they should act like cosmic blowtorches, ionizing and heating gas across millions of light years. Models suggest this process, called feedback, ought to have left the intergalactic medium simmering at tens of millions of degrees. But real-world observations show gas temperatures closer to 100,000 degrees orders of magnitude cooler. Where did all that missing energy go? One clue lies in the CXB's unresolved component. If a significant fraction comes from faint, overlooked sources like wandering black holes or dim AGN, their emissions might be less efficient at heating surrounding gas. Unlike their brighter cousins, these underachievers could leak energy in softer, less penetrating X-rays, like a heater set to low simmer rather than full blast. Another possibility involves the cosmic web structure. The filaments and voids threading the universe aren't just passive conduits, they might behave like a labyrinth, trapping and redistributing energy in ways we haven't accounted for. Imagine pouring hot water into a sponge. Some heat radiates outward, but much of it gets absorbed, lingering in hidden pockets. Similarly, X-rays from AGN could be soaking into dense filamentary gas, their energy dissipating locally rather than flooding the voids. This would explain why some galaxy clusters show scorching hot halos while the space between them remains relatively cool. The cosmic X-ray background's patchy, uneven distribution supports this idea, hinting at an energy recycling system far more complex than our models assume. Then there's the wild card of magnetic fields. These invisible force lines stretched across megaparsecs could act like cosmic insulation, preventing X-rays from uniformly heating intergalactic gas. Charged particles guided by magnetic fields might channel energy along specific paths, leaving vast regions untouched. It's akin to heating a house with a broken HVAC system. Some rooms roast while others stay icy. The CXB's spectral irregularities, particularly its excess of soft X-rays, align eerily with simulations where magnetic fields redirect and scatter high-energy photons. The most tantalizing explanation: we might be underestimating the universe's ability to shed heat. Some theories propose that dark energy, the mysterious force accelerating cosmic expansion, could also act as a coolant, sapping thermal energy from intergalactic gas over time. Others suggest undiscovered particles, like sterile neutrinos, might carry away excess heat like invisible radiators. If true, the cosmic X-ray background's spectral fingerprints could reveal these processes in action, offering a window into physics beyond the standard model. What makes this mystery so crucial is its ripple effect. If black hole feedback is weaker than predicted, it changes how we model galaxy formation, star birth, even the distribution of dark matter. The cosmic X-ray background isn't just a relic of high-energy events, it's a ledger of the universe's energy budget, and right now the books aren't balancing. Every unexplained photon in its glow hints at forces we've yet to name, quietly shaping the cosmos in ways we're only beginning to glimpse. What if the cosmic X-ray background isn't just about black holes and hot gas, but particles so exotic they rewrite the rules of reality? This is where astrophysics collides head-on with quantum mysteries, as scientists chase the tantalizing possibility that some CXB photons might come from realms beyond the standard model. Among the prime suspects, sterile neutrinos, hypothetical particles that could solve two cosmic puzzles at once, dark matter's identity and the X-ray background's lingering enigmas. Picture a universe filled with invisible particles trillions of times more abundant than atoms, yet barely interacting with ordinary matter. Sterile neutrinos, unlike their detectable cousins, would rarely bump into anything, drifting through planets and stars like ghosts. But according to some theories, these particles could occasionally decay into active neutrinos and X-ray photons, leaving a faint but measurable signal in the cosmic background. The math is eerily precise. If sterile neutrinos make up even a fraction of dark matter, their decays would produce X-rays at very specific energies around 3.5 kiloelectronvolts. And here's the kicker: multiple telescopes, including XMM Newton and Chandra, have detected an unexplained emission line at exactly this energy in galaxy clusters and the Milky Way's halo. It's like finding a signature at a crime scene that matches only one suspect's handwriting, yet not everyone's convinced. Alternative explanations abound, from sulfur ions in hot gas to exotic plasma physics. The signal's weakness makes it prone to instrumental noise, and follow-up observations have yielded conflicting results. Some teams claim the line vanishes when accounting for all background sources. Others insist it persists, flickering in unexpected places like Andromeda's core. The debate highlights a deeper truth. Hunting for particle physics in the CXB is like listening for a whisper in a hurricane. Even if sterile neutrinos exist, their signal could be drowned out by astrophysical sources, forcing researchers to chase statistical anomalies across petabytes of X-ray data. But sterile neutrinos aren't the only quantum players in this drama. Actions, another dark matter candidate, could convert to X-rays when skirting black holes' intense magnetic fields. Certain string theory variants predict hidden sector particles that decay into high-energy photons, potentially contributing to the CXB's unresolved flux. Then there's the radical idea that primordial black holes, those hypothetical leftovers from the Big Bang, might evaporate via Hawking radiation, spraying X-rays as they vanish. Each theory leaves a distinct fingerprint in the cosmic background spectrum, offering a treasure map for next-generation detectors. The stakes couldn't be higher. If even a sliver of the CXB traces back to exotic particles, it would revolutionize both astrophysics and quantum theory, bridging the gap between the cosmos' largest structures and its smallest constituents. But until we untangle these signals from the noise, the particle physics connection remains a tantalizing what if a reminder that the universe's greatest mysteries might hide not in distant galaxies, but in the quantum shadows between them. The cosmic X-ray background holds yet another curveball, one that twists our understanding of high-energy light itself. Deep within its glow, astronomers have stumbled upon something utterly unexpected: faint but detectable polarization, a property that reveals whether electromagnetic waves vibrate in orderly patterns or chaotic directions. Most X-ray sources produce unpolarized radiation, their photons scattering every which way like a crowd dispersing after a concert. But certain patches of the CXB show subtle alignment, as if something out there is quietly organizing the chaos. This isn't just a minor detail, it's a clue that the universe's largest magnetic fields or most exotic emission mechanisms might be hiding in plain sight. Picture dropping a handful of needles onto a table. Normally, they'd land in random orientations, but if you found them all pointing northeast, you'd suspect a magnet beneath the surface. That's the essence of the polarization surprise. When instruments like NASA Imaging X-ray Polarimetry Explorer (IXP) trained their sights on the CXB, they expected to measure barely any polarization, perhaps a percent or two from known sources like scattering by interstellar dust. Instead, some regions showed polarization levels up to 10%, far exceeding predictions. The implication: either colossal magnetic fields stretching across intergalactic space are aligning X-rays like invisible hands guiding compass needles, or entirely new physics is at play in how these high-energy photons are born. One explanation points to the cosmic web's hidden magnetic architecture. Simulations suggest that during the universe's violent youth, shocks from galaxy formation and black hole jets could have amplified primordial magnetic fields, weaving them into filaments millions of light-years long. If these fields persist, they might subtly polarize X-rays passing through, imprinting order onto the background's apparent chaos. Yet even this dramatic scenario struggles to account for the observed signal's strength. The energy required to maintain such vast, coherent fields defies current models, like finding a power grid the size of a continent operating without any visible power plants. Then there's the wild card. Certain active galactic nuclei might be polarizing X-rays in ways we've never seen. Most AGN emit unpolarized radiation, but if their accretion disks warp under extreme conditions, or if their jets twist into helical structures, they could produce beamed, polarized X-rays that dominate patches of the background. It's akin to spotting a spotlight in a sea of light bulbs. Its focused beam would stand out against the diffuse glow. The challenge: no known AGN exhibits polarization this intense, suggesting either a rare subclass we've yet to catalog or a fleeting phase in black hole evolution where polarization spikes temporarily. The most radical theories venture beyond conventional astrophysics. Some quantum gravity models predict that spacetime itself, at microscopic scales, could bend X-ray photons in ways that mimic polarization. Others propose that dark matter particles, when colliding, might emit polarized X-rays as they annihilate. These ideas sit at the frontier of science, difficult to test but impossible to ignore when faced with data that defies mainstream explanations. What makes this mystery so transformative is its reach. Polarization isn't just a curiosity, it's a diagnostic tool revealing the hidden forces shaping the cosmos. Every percentage point of unexpected alignment in the CXB forces us to reconsider how energy flows, how fields intertwine, and how the universe imposes order on its grandest scales. And until we decode its origins, this quiet twist in the X-ray sky remains one of the cosmos' most eloquent unsolved riddles. At the heart of our galaxy lies a cosmic contradiction, a shadow where none should exist. When scientists mapped the cosmic X-ray background toward the Milky Way's core, they expected to find the glow dimmed by dense clouds of gas and dust, the same way a hand blocks sunlight when held up to a lamp. Instead, they discovered something far stranger: regions where the background X-rays vanish completely, as if swallowed by an invisible void. This galactic shadow defies every model of how our galaxy should interact with high-energy light, revealing gaps in our understanding of the Milky Way's turbulent heart. The mystery begins with scale. The galactic center is a maelstrom of superheated gas, supernova remnants, and of course Sagittarius A, our resident supermassive black hole. All this chaos should absorb and scatter background X-rays unevenly, some areas dimmer, others brighter due to complex interactions. Yet the observed shadow is too deep, too crisp, as if something far more structured than random gas clouds is at work. Imagine shining a flashlight through fog. you'd expect a diffuse halo, not a razor-sharp silhouette. That's precisely what telescopes like Chandra and New Star are seeing. An X-ray shadow so stark it suggests the presence of a cold, dense barrier we've yet to identify. One theory points to a titanic disk of molecular gas swirling just beyond Sagittarius A. This disk, if thick and cold enough, could act like a cosmic umbrella, blocking background X-rays while remaining nearly invisible itself. But here's the catch. No known gas structure in the Milky Way has the right density and orientation to cast such a perfect shadow. Even the famed central molecular zone, a ring of dense gas orbiting the core, doesn't align neatly with the shadow's edges. It's like blaming a tree for blocking the sun when the shadow's shape matches no tree you've ever seen. Then there's the black hole's role. Sagittarius is relatively quiet today, but evidence suggests it was a ferocious X-ray source in the past. Some researchers propose that ancient outbursts, jets or winds from the black hole's active phase could have carved cavities in the surrounding gas, leaving tunnels where background X-rays stream through unimpeded. But this raises new questions. Why haven't these cavities filled in over time? And why do they align so precisely to create shadowed regions now? The timing seems improbably convenient, like finding footprints in mud that somehow never washed away despite centuries of rain. The most tantalizing possibility involves magnetic fields. Near the galactic center, magnetic forces are strong enough to twist gas into bizarre filamentary structures, some stretching dozens of light years. If these filaments organized into a kind of labyrinth wall, they could deflect or absorb X-rays in specific directions, creating shadowed patches. It's a stretch, but not impossible. We've already seen magnetic fields shape stranger things, like the bizarre radio bubbles towering above the Milky Way. What makes this shadow so unnerving isn't just its existence, it's what it implies about our blindness to the galaxy's anatomy. We're like cartographers mapping a forest by listening to echoes, only to stumble upon a clearing that shouldn't be there. Every unexplained dip in the X-ray background whispers that the Milky Way's core holds structures darker, colder, and more intricate than our telescopes have yet revealed. And until we solve this riddle, the galactic center's shadow will loom as a silent reminder. Sometimes the cosmos hides its secrets not in light but in the absence of it. Galaxy clusters should be powerhouses of X-ray emission, gigantic cauldrons of superheated gas trapped in the grip of dark matter's gravity, glowing fiercely in high-energy light. According to every simulation, these clusters ought to be major contributors to the cosmic X-ray background, their combined output forming a significant chunk of its unresolved glow. Yet when astronomers tally up real-world observations, the numbers refuse to cooperate. The discrepancy isn't minor. It's a gaping chasm between prediction and reality, forcing scientists to question whether we understand clusters at all. Take the Coma cluster, one of the most massive structures in our cosmic neighborhood. Its central gas, heated to nearly 100 million degrees, blazes with X-rays. Multiply that by the thousands of known clusters across the universe, and you'd expect a staggering contribution to the CXB. But when researchers sum the emissions from all observed clusters, they account for less than 20% of the expected signal. It's like calculating the total light from every city on Earth, only to find it's barely enough to explain the moon's brightness. Where's the missing energy? One possibility cuts straight to the heart of modern cosmology. What if galaxy clusters are leaking energy? Simulations assume that once gas falls into a cluster's gravitational well, it stays there, steadily heating up. But real clusters might be far messier dynamic environments where turbulence, magnetic fields, and sloshing motions siphon off energy into invisible channels. Picture a boiling pot with a loose lid. Steam escapes before you can measure it all. Similarly, clusters could be losing X-rays to vast, undetectable outflows or converting their thermal energy into particle acceleration, leaving less to contribute to the background. Then there's the puzzle of missing clusters. Our surveys might be overlooking an entire population of faint, diffuse clusters, cosmic ghosts too dim to spot with current telescopes. These stealthy structures could be hiding in plain sight, their gas too spread out to emit strongly but numerous enough to collectively fill the gap. Imagine trying to census a forest by counting only the tallest trees. You'd miss the understory entirely. If such clusters exist, next-generation X-ray observatories like Lynx or Athena might finally reveal them, but for now they're theoretical phantoms. The plot twists further when we examine the clusters we can see. Some show X-ray emissions far hotter than models predict, as if some unseen force is cranking up the temperature. Others flicker unpredictably, their brightness changing too fast for traditional explanations. A subset even exhibits bizarre, cold fronts, sharp boundaries where gas temperatures plummet, defying the smooth gradients expected in relaxed clusters. These anomalies suggest that clusters aren't the serene, well-behaved systems we once thought. Instead, they might be cosmic battlegrounds where mergers, shock waves, and dark matter interactions constantly reshape their energy output. The most radical explanation, our understanding of plasma physics itself might be flawed. The gas in clusters isn't just hot, it's ionized, threaded with magnetic fields, and seething with turbulence. Standard models treat this plasma as a simple fluid, but real-world conditions could trigger poorly understood phenomena like anomalous heat conduction or particle acceleration. If energy dissipates in ways we haven't accounted for, it would throw off every calculation of clusters' X-ray contributions. It's like trying to predict the sound of an orchestra by studying only the violins. The cluster controversy isn't just academic. If simulations overestimate their role in the CXB, it implies that other, more exotic sources must be lurking in the shadows. Perhaps the elusive warm-hot intergalactic medium, or even particle decay from dark matter. Every mismatch between theory and observation forces us to widen the search, probing deeper into the high-energy universe's hidden layers. And until we solve this puzzle, galaxy clusters will remain both landmarks and mirages in our maps of the X-ray sky, bright beacons that still can't account for the light they should be casting. Binary stars shouldn't steal the cosmic spotlight, yet in some galaxies, they're doing exactly that. Among the usual suspects behind the cosmic X-ray background, supermassive black holes, hot gas, distant quasars, there's an unexpected player, X-ray binary stars, and not just a few, but entire swarms of them, churning out far more high-energy light than anyone predicted. These aren't your average stellar duos, they're cosmic power couples where one star strips material from its companion, funneling it into a neutron star or black hole and igniting violent X-ray flares. Normally, they're background extras in the galactic drama, but in certain galaxies they've become the lead actors, flaring so brightly and abundantly that they might rewrite our playbook on stellar evolution and reshape our understanding of the CXB's unresolved glow. Take the starburst galaxy M82, a chaotic nursery of newborn stars just 12 million light-years away. While most galaxies produce X-rays from their central black holes or supernova remnants, M82's X-ray signature is dominated by something else: dozens of X-ray binaries, some shining hundreds of times brighter than typical systems in common galaxies like our own. It's as if the Milky Way's occasional X-ray fireworks had been replaced by a non-stop pyrotechnic display. The reason? Starbursts like M82 forge massive stars at breakneck speeds, and massive stars die young, often leaving behind neutron stars or black holes that quickly pair up with surviving siblings. The result is a surplus of X-ray binaries, each one a miniature furnace of high-energy light. But here's where the plot twists. These binaries aren't just numerous, they're different. In quieter galaxies, X-ray binaries fade as their fuel runs low, but in starburst environments, fresh stellar winds and supernova shocks constantly feed them new material, keeping them active far longer than models predict. Some even seem to defy the Eddington limit, the theoretical maximum brightness a star can achieve before radiation blows away its fuel supply. Yet in M82 and its ilk, they burn brighter and longer, as if playing by an entirely new set of rules. If such galaxies were rare, we might dismiss them as cosmic oddities, but recent surveys suggest they're more common than we thought, especially in the early universe, where star formation raged at rates dwarfing even modern starbursts. The implications for the cosmic X-ray background are profound. If galaxies like M82 were widespread in the past, their binary populations could have flooded the young universe with X-rays, contributing to the diffuse glow we see today. This would solve a key puzzle: why the CXB's unresolved portion skews toward softer, lower-energy X-rays, much like the output of binary stars rather than the harder emissions of supermassive black holes. It's like realizing a distant city's nighttime glow comes not from skyscrapers but from countless streetlights, each faint on its own but collectively transformative. Yet this revelation opens new cans of worms. For one, it challenges our models of binary star formation. Why do some galaxies spawn so many of these systems? Is it the sheer density of stars in starbursts or something about their chemical makeup? Then there's the question of feedback. If X-ray binaries were this abundant in the early universe, their radiation might have sterilized surrounding gas, suppressing future star formation in ways we've never accounted for. The cosmic X-ray background, once seen as a passive relic, suddenly becomes an active sculptor of galactic evolution. The deeper we dig, the clearer it becomes. What seemed like a side note in astrophysics might be a central chapter. X-ray binaries, long relegated to the footnotes of high-energy astronomy, could hold the key to balancing the CXB's energy ledger, and in doing so, expose how much we've underestimated the quiet power of stellar partnerships. The universe, it seems, has been keeping double ledgers all along. Light travels fast, but not infinitely fast, and that simple fact might hold the key to one of the cosmic X-ray background's most perplexing features. Picture a quasar, one of the universe's most luminous objects, screaming X-rays into the void billions of years ago. Those photons didn't just race straight to our telescopes. Some took detours, bouncing off intergalactic gas clouds, scattering across filaments of the cosmic web, and arriving at Earth eons later than their direct path counterparts. What if the CXB's unresolved glow isn't just from hidden sources, but from these ancient echoes reverberating through cosmic time like whispers in a cavern? This light echo theory turns conventional wisdom on its head. Normally, we assume a telescope's view of the distant universe is frozen in time, a snapshot of how things looked when the light departed. But the CXB's diffuse nature suggests a messier reality. Imagine shouting into a canyon and hearing your voice return not as a single echo, but as a chorus of overlapping reflections from cliffs at different distances. Similarly, X-rays from a single quasar outburst could reach us via multiple routes, each path leaving its own timestamp in the cosmic background. Some photons arrive promptly, while others, scattered by gas clouds hundreds of thousands of light-years wide, trickle in much later, smearing the quasar's signal across millennia. The math gets even wilder when you consider scale. A quasar's X-rays might first illuminate a nearby gas cloud, then bounce to another farther out, zigzagging through intergalactic space before finally heading toward Earth. Each interaction steals a bit of energy, softening the X-rays and blending them into the CXB's unresolved haze. Over cosmic timescales, these delayed photons could outnumber the original direct emissions, like hearing more echoes than the initial shout. Telescopes would struggle to link them back to their sources, leaving us with a sky full of ghostly X-rays untethered from visible objects. Yet proving this theory is like reconstructing a symphony from a single note. The echoes would be faint, their energies subtly altered by each scattering event. The best evidence comes from shadowing experiments, where astronomers study how quasars backlight intervening gas clouds. Some clouds show unexpected X-ray fluorescence glowing not from their own energy, but from quasar light absorbed and re-emitted long after the primary beam passed through. It's as if you shined a flashlight through fog and minutes later, patches of mist still glowed from trapped photons finally escaping, but the echo's biggest hurdle is time. For this process to explain a significant chunk of the CXB, the universe would need an army of reflectors of vast, ionized gas structures positioned just right to catch and redirect quasar light over billions of years. While the cosmic web provides potential scaffolding, the fine-tuning required beggars belief. Why would so many gas clouds align so precisely to create this delayed chorus? Unless, of course, we're missing something fundamental about how matter organizes itself across intergalactic space. The quasar echo idea forces us to confront a radical notion that the cosmic X-ray background isn't just a static image of the universe's high-energy sources, but a palimpsest, a layered record of emissions stretched and smeared across time. Every unexplained wisp of X-rays could be a message from two epochs at once, the moment a quasar flared and the moment its light finally found its way to us. If true, it means our maps of the X-ray sky aren't just incomplete, they're out of sync, with the past and present superimposed in a single, shimmering veil of light. The universe's missing matter hides in plain sight, not cloaked in darkness, but adrift in a ghostly sea of superheated gas so diffuse it slips through our telescopes like mist through a net. The warm-hot intergalactic medium, or WIM, is the theoretical backbone of cosmology, accounting for up to half the universe's normal matter. Yet its presence in the cosmic X-ray background remains stubbornly elusive, like a fingerprint left in steam. Scientists know it must be their simulations show the cosmic web's filaments pulsing with million-degree gas, but turning theory into ironclad detection has become one of modern astronomy's most frustrating games of hide and seek. Picture trying to photograph a snowstorm one flake at a time. The WIM extreme thinness, just a few atoms per cubic meter, means its X-ray glow is laughably faint compared to dazzling sources like quasars or galaxy clusters. Even worse, its signature blends with foreground interference from our own galaxy's hot halo and the solar wind's charged particles. It's like listening for a whisper while standing next to a jet engine. The few possible detections, like XMM Newton's 2017 observation of a filament between galaxy clusters, hover tantalizingly close to the noise floor, leaving room for skeptics to argue they're just statistical flukes. The challenge isn't just sensitivity, it's spectroscopy. To confirm WIM, astronomers need to identify specific absorption lines in the CXB's spectrum where intergalactic oxygen and neon ions have soaked up X-rays at precise energies. But these lines are absurdly narrow, requiring instruments with resolution far beyond current technology. Imagine trying to measure the thickness of a single hair from 10 miles away. Even Chandra, our sharpest X-ray eyes, struggles to separate these subtle dips from instrumental artifacts. Compounding the problem, WIM uneven distribution means its signal flickers across the sky, strong where filaments intersect, nearly absent in voids, making it impossible to study with broad, shallow surveys. Yet the hunt continues because the stakes couldn't be higher. If WIM exists as predicted, it validates decades of cosmic web simulations and solves the missing baryon problem in one stroke. If it doesn't, we're forced to confront a terrifying possibility that half the universe's normal matter has simply vanished, or worse, that our fundamental models of gas thermodynamics are deeply flawed. New hope lies with upcoming missions like Athena, whose microcalorimeters promise spectroscopy fine enough to finally catch WIM whisper. Until then, this phantom ocean remains the cosmic X-ray background's most consequential ghost, a shadow empire of matter we know must exist if only we could learn to see it. Even the most advanced X-ray telescopes have an Achilles heel, an invisible layer of uncertainty woven into their very design. When it comes to measuring the cosmic X-ray background, the instruments themselves might be distorting the data in ways we're only beginning to grasp. Imagine trying to measure the temperature of a candle flame with a thermometer that unpredictably drifts between scorching and freezing. That's the calibration conundrum haunting CXB research. The challenge isn't just about precision. It's about untangling whether the mysteries we see are written in the fabric of the universe or etched into the lenses of our telescopes. Take the delicate matter of detector efficiency, the ability of an X-ray telescope to accurately count photons at different energies. Over time, exposure to intense radiation can subtly degrade these detectors, like sunscreen wearing off under relentless sunlight. A sensor that once registered 90% of incoming X-rays might drop to 85% after years in space, silently skewing measurements of the background's intensity. Compounding this, each telescope has unique blind spots energy ranges where its sensitivity plummets, creating artificial dips in the observed spectrum. It's like listening to a symphony with intermittent hearing loss. Certain notes vanish, leaving gaps that might masquerade as cosmic phenomena. Then there's the puzzle of stray light photons that bounce off internal telescope structures like ricocheting bullets, landing in detectors where they don't belong. For bright sources like active galaxies, this noise is easy to filter out. But for the CXB's diffuse glow, which is already a whisper against the instrument's own electronic hum, stray light can inflate measurements by up to 10%. Scientists spend months modeling these effects using dummy observations of blank sky regions, but the corrections rely on assumptions that might not hold across the entire energy range. It's akin to correcting a blurry photo. You can sharpen the image, but some details might be artifacts of the process itself. The plot thickens with cross-calibration disputes between observatories. When Chandra, XMM Newton, and Suzaku all observed the same patch of sky, their CXB flux measurements disagreed by as much as 15%, a variance larger than some of the anomalies they're trying to explain. Part of this stems from differing energy resolutions. One telescope might split X-rays into 50 distinct energy bins, while another uses 20, smearing subtle spectral features. Other discrepancies trace back to how each mission defines its zero level, the baseline darkness against which the CXB is measured. Like musicians tuning to different reference pitches, these variations create dissonance in what should be a harmonious dataset. Perhaps most troubling are the ghost signals, instrumental artifacts that mimic real astrophysics. Certain detector materials fluoresce when struck by high-energy particles, emitting X-rays at precise energies that match common emission lines. Without meticulous screening, these false signals could be mistaken for evidence of warm intergalactic gas or even exotic dark matter decays. Even cosmic rays, charged particles raining down from deep space, can trigger detector pixels at random, creating a snowstorm of noise that obscures the true CXB. Filtering out this interference is a never-ending game of whack-a-mole, with each solved problem revealing new layers of complexity. Yet this isn't just a technical headache, it's a philosophical challenge. How much of the CXB's mysteries are actually reflections of our own limitations? The answer might lie in next-generation calibrators like NASA's upcoming Lynx mission, which plans to use neutron star atmospheres as natural X-ray candles, standardized light sources against which all instruments can be benchmarked. Until then, every measurement of the cosmic X-ray background carries an invisible asterisk, reminding us that sometimes the greatest obstacles to understanding the universe aren't in the distant cosmos, but in the mirrors we've built to observe it. When astronomers overlay maps of the cosmic X-ray background with other cosmic emissions like the infrared glow of dusty galaxies or the microwave whisper of the Big Bang's afterglow, something peculiar emerges. Patterns align where they shouldn't. Faint tendrils of correlation weave between these seemingly unrelated phenomena, as if the universe is hinting at connections deeper than our models can explain. These cross-correlations aren't just statistical blips, they're cosmic breadcrumbs pointing toward hidden relationships between the high-energy and low-energy realms of the cosmos. Take the infrared X-ray connection. At first glance, the two should have little to do with each other. Infrared light comes from cool dust and aging stars, while X-rays scream from superheated gas and violent black holes. Yet when researchers compared data from NASA's Spitzer Space Telescope with X-ray surveys, they found a surprising synchronicity. Regions rich in infrared emissions often coincided with patches of elevated X-ray background. It's like discovering that the hum of a refrigerator correlates with the roar of a jet engine, a pairing that defies intuition. One explanation: both signals might trace back to active galactic nuclei, where black holes heat surrounding dust to infrared temperatures while also blasting X-rays from their accretion disks. But the match isn't perfect. Some infrared bright zones show no corresponding X-ray boost, and vice versa, leaving gaps in the narrative. Even stranger is the X-ray background's flirtation with the cosmic microwave background, the relic radiation from the Big Bang. The CMB is the oldest light in the universe, a snapshot of a time before galaxies or stars existed. By all rights, it should have no business correlating with the much younger X-ray background. Yet subtle statistical analyses reveal a faint but persistent link, particularly in large-scale structures like galaxy clusters. One theory suggests this is the imprint of the Sunyaev-Zeldovich effect, where CMB photons gain energy as they pass through hot cluster gas, subtly shifting the microwave background spectrum. But the effect's strength varies wildly, with some clusters showing far stronger X-ray CMB ties than their gas content should allow. Then there's the dark matter angle. Certain models predict that if dark matter particles decay or collide, they could produce both X-rays and subtle distortions in other cosmic backgrounds. Imagine dark matter as a cosmic middleman, mediating an unseen conversation between high-energy and low-energy light. While no smoking gun has been found, the mere possibility forces astronomers to reconsider whether the CXB's unresolved features are echoes of the universe's most elusive substance. These cross-correlations are more than curiosities, they're fractures in the walls between astrophysical disciplines. Every unexpected alignment whispers that our compartmentalized view of the cosmos might be obscuring a grander, more interconnected reality. And until we decode these hidden handshakes between light and shadow, the universe will keep nudging us toward truths we've yet to imagine. The universe's chemistry doesn't add up. When massive stars explode as supernova, they should be scattering heavy elements, iron, oxygen, silicon, across space like cosmic shrapnel. These metals, heated to millions of degrees, ought to glow brightly in X-rays, leaving an unmistakable fingerprint on the cosmic X-ray background. Yet when astronomers tally up the expected signal, it's barely a whisper. Where are all the missing metals? This isn't just a bookkeeping error. It's a full-blown cosmic contradiction, forcing us to question how elements move, hide, and interact in the spaces between galaxies. Start with what we know. Every supernova is a forge, smelting elements heavier than hydrogen and helium and blasting them outward at thousands of kilometers per second. Over billions of years, these metals should have suffused the intergalactic medium, mixing with pristine gas to form a diffuse, hot soup detectable by its X-ray emissions. Simulations predict a sky threaded with the spectral signatures of iron and oxygen ions, specific energy spikes where these atoms absorb or emit X-rays. But when telescopes like Chandra and XMM Newton scour the CXB for these telltale lines, they come up shockingly empty. It's as if someone took a bucket of paint, threw it into the wind, and found no trace of color on the ground. One explanation is that the metals aren't missing, they're hiding in plain sight. Imagine pouring molten gold into a glacier. The gold wouldn't vanish, but it might freeze into countless tiny flecks too small to spot from a distance. Similarly, heavy elements could be locked up in ultra-fine dust grains or cool, dense gas clouds invisible to X-ray telescopes. Some might even cling to dark matter's invisible scaffolding, trapped in filaments too tenuous to emit detectable radiation. There's precedent for this. Observations of distant quasars show their light dimmed by intervening metal-rich gas, proving the elements are out there, just not glowing as expected. Then there's the escape theory. Supernova explosions aren't just dispersing metals, they're propelling them at velocities high enough to break free from their host galaxies entirely. Like sparks from a firework vanishing into the night, these elements might be ejected so far into intergalactic voids that they've diluted beyond detection. Computer models suggest this galactic wind effect could be especially potent in the early universe, where frequent supernova and weaker gravity allowed metals to flee into the cosmic wilderness. But even this can't fully explain the discrepancy. The winds would have left traces vast, metal-enriched bubbles around galaxy clusters, yet these structures remain elusive in X-ray maps. The most tantalizing possibility, we're misreading the metal's language entirely. Normally, we assume ionized iron and oxygen emit X-rays when heated. But in environments with extreme radiation or bizarre magnetic fields, these atoms might behave differently, radiating energy in unexpected ways or even quenching their emissions entirely. Picture a chameleon not just changing color but becoming transparent under the right light. Certain quantum physics models suggest heavy elements in the deepest voids could exist in exotic states, their electron shells rearranged by eons of isolation, rendering them spectroscopically invisible to our instruments. This isn't just an academic puzzle. Metals are the building blocks of planets' life, even the tools we use to study the cosmos. If they're vanishing from our X-ray maps, we're missing a crucial chapter in the story of how the universe organizes its matter. Every undetected atom is a clue not just to where the elements went, but to the forces shaping the spaces between the stars. The cosmic X-ray background silence might be its loudest message yet. The universe is far stranger, far sneakier than we ever imagined. Dark matter has always played the cosmic phantom, its presence felt through gravity's pull on galaxies, yet never directly seen. But what if its shadow isn't completely silent? Hidden within the cosmic X-ray background's unexplained glow, there might be a whisper of dark matter's demise, the faintest flicker of particles unraveling into high-energy light. This isn't just speculative physics, it's a tantalizing thread connecting two of the universe's greatest mysteries. The theory hinges on a radical proposal. Certain dark matter particles, when they collide or decay, could produce X-rays as a byproduct. Imagine a vast, invisible ocean where occasional ripples manifest as bursts of light. Only here, the ocean is the dark matter halo enveloping our galaxy, and the light is X-rays blending into the cosmic background. The most compelling candidate, sterile neutrinos, ghostly particles heavier than their ordinary cousins, with just enough mass to decay into an X-ray photon and an ordinary neutrino. If they exist, their collective decays would leave a spectral signature at a very specific energy, around 3.5 kiloelectronvolts, and that's where things get eerie. Multiple X-ray telescopes, including XMM Newton and Chandra, have detected an unexplained emission line at exactly this energy, threading through galaxy clusters and the Milky Way's halo like a cosmic breadcrumb trail. But the plot thickens. This signal isn't uniform, it's strongest in regions where dark matter should clump most densely, like the centers of galaxies or the Perseus cluster, a massive gathering of galaxies bound by dark matter's grip. It's as if the universe is subtly underlining the connection, placing the X-ray fingerprints precisely where detectives would expect to find them, yet skeptics aren't ready to call it proof. Alternative explanations abound: sulfur ions in hot gas, plasma physics anomalies, or even instrumental quirks could mimic the signal. The debate rages because the stakes are so high. If this line truly marks dark matter's decay, it would be the first direct evidence of its particle nature, a Nobel Prize-worthy breakthrough. If not, it's a cosmic mirage luring us down a dead-end path. The challenge is unlike any other in astrophysics. Dark matter's sheer elusiveness means even its hypothetical decays would be staggeringly rare. A single sterile neutrino might take billions of years to decay, making its X-ray whisper vanishingly faint against the cacophony of black holes and supernova. Detecting it requires sifting through mountains of data for the faintest statistical bump, like searching for one unique grain of sand on a beach. And even if the signal is real, it raises new puzzles. Why 3.5 kiloelectronvolts? Why don't we see similar lines at other energies? The answers might lie in the intricate physics of particle decay, or they might hint at dark matter's even stranger behaviors, perhaps interactions with magnetic fields or quantum effects we've yet to imagine. What makes this hypothesis so captivating isn't just its potential to solve two mysteries at once: the nature of dark matter and the origin of the CXB's unresolved glow, but its audacity. It dares to bridge the gap between the infinitesimally small and the astronomically vast, suggesting that the key to understanding galaxy clusters and cosmic structure might lie in the quantum shudder of a single, elusive particle. Until we know for sure, the cosmic X-ray background remains both a map and a riddle, its faintest lines holding the universe's best-kept secrets. The future of cosmic X-ray astronomy isn't just about sharper images, it's about rewriting the rules of discovery. Decades of puzzling over the cosmic X-ray background's enigmas have set the stage for a revolution, with next-generation telescopes poised to tear through the veil of uncertainty like never before. At the forefront is ESA's Athena, the advanced telescope for high-energy astrophysics, slated for launch in the mid-2030s. This behemoth isn't just an upgrade, it's a paradigm shift. With a mirror assembly boasting 10 times the collecting area of current X-ray observatories and microcalorimeters capable of measuring photon energies with razor precision, Athena could finally isolate the whisper of warm-hot intergalactic gas in the cosmic web, or catch sterile neutrino decays red-handed. Its spectral resolution will be so fine, scientists liken it to distinguishing every instrument in an orchestra from a single note. But Athena isn't flying solo. NASA Lynx mission, still in the concept phase, promises even wilder capabilities. Designed to peer back to the universe's first black holes, Lynx's ultra-high-resolution imagers could resolve thousands of currently invisible X-ray sources per square degree, turning the CXB's unresolved fog into a starfield of individual emitters. Picture a microscope zooming in on fog to reveal it's actually made of countless droplets. That's Lynx's potential. Its proposed grating spectrometers would dissect X-rays with such fidelity they could map the velocity of gas flows around distant quasars, exposing how energy propagates through the cosmic web. Together, Athena and Lynx could corner the missing baryon problem, trapping the elusive whim between their crosshairs by combining wide-field surveys with deep, needle-in-a-haystack precision. Meanwhile, China's Einstein probe, launching this decade, brings a different superpower: time. Sporting lobster-eye optics that granted a panoramic view of the X-ray sky, this mission will monitor the cosmos for fleeting flares and eruptions, ideal for catching ULXs in their explosive acts or spotting dormant black holes flickering to life. If the CXB's variability has taught us anything, it's that the universe loves surprises. Einstein probe's real-time alerts could reveal entire populations of transient X-ray sources we've overlooked, like turning on a blacklight in a dark room to uncover hidden graffiti. The game-changer, though, might lie in the synergy of these missions with multi-wavelength surveys. Imagine correlating Athena's X-ray maps with the Rubin Observatory's optical sky scans or JWST deep infrared vistas. Suddenly, those mysterious X-ray shadows near the galactic center could be matched to cold molecular clouds seen in radio waves, or faint infrared galaxies hiding behind dust. The European Space Agency's upcoming Ariel mission, focused on exoplanet atmospheres, might seem an odd partner, but its infrared spectra could accidentally spot the heat signatures of galaxies obscuring their X-ray AGN, solving the missing source paradox. And then there's the wild card, quantum-enabled detectors. Labs are already testing superconducting sensors that could one day measure single X-ray photons with zero noise, pushing energy resolution beyond current limits. Pair these with AI-driven analysis tools sifting through petabytes of data for subtle correlations, and the CXB's secrets might unravel in ways we can't yet predict. The cosmic X-ray background has spent half a century defying explanations, but the next decade of telescopes won't just seek answers, they'll redefine the questions. The greatest mystery might be how much we don't yet know we're missing. After 25 mind-bending mysteries, one truth becomes undeniable. The cosmic X-ray background isn't just a scientific puzzle to solve. It's a mirror reflecting how little we truly grasp about the universe's high-energy drama. From missing matter to flickering shadows, from invisible black holes to whispers of dark matter's decay, every layer we peel back reveals deeper questions, forcing us to confront the humbling reality that our cosmic maps are still riddled with blank spaces. Consider this: we've spent decades building detectors, launching telescopes, and refining models, yet roughly half the CXB's glow remains unaccounted for. That's like assembling a jigsaw puzzle only to realize half the pieces belong to a different picture entirely. The unresolved portion isn't just background noise, it's a chorus of cosmic phenomena we've either overlooked or haven't yet imagined. Somewhere in that haze could be answers to questions we're not even smart enough to ask yet. Take the way these mysteries intertwine. The missing baryons problem isn't separate from the WIM elusiveness. The enigma of obscured AGN isn't distinct from the early universe's X-ray excess. They're threads in the same tapestry, each tugging at our understanding of how energy, matter, and structure weave together across billions of years. Even the calibration challenges and instrumental limits plaguing our measurements aren't mere technicalities, they're reminders that the universe doesn't owe us easy answers. What's most thrilling isn't just the mysteries themselves, but what they imply about the road ahead. Every time we've assumed we're nearing completion, that one more telescope, one more algorithm, will finally solve the CXB, the cosmos laughs and reveals another layer of complexity. The greatest lesson here might be that the universe's most profound truths aren't hiding in the glaring light of quasars or the violent bursts of supernova, but in the quiet, persistent glow we've spent decades dismissing as mere static. So here's the question that lingers: if we've barely scratched the surface of the cosmic X-ray background, what other invisible symphonies are playing just beyond our perception? What cosmic revolutions are waiting in the unresolved light, ready to rewrite physics as we know it? The hunt isn't just about filling gaps, it's about discovering that the gaps themselves were the point all along. And the next chapter, it's being written right now in the data streams of telescopes old and new, in the notebooks of theorists chasing wild ideas, and perhaps in the curiosity of everyone who's ever looked up at the night sky and wondered what secrets it's still keeping.